What if the most successful scientific theory ever built is also a sign that something has gone profoundly wrong? Not wrong in the way a rough draft is wrong, not wrong in the way early maps were wrong, where the coastlines were approximate and the interiors were guesswork. Wrong at the foundation, wrong in the way that says the entire architecture needs to be examined from the ground up because the ground itself is not what we assumed it was. Physics is the most precise, most verified, most consequential intellectual enterprise in human history. That is not an overstatement. We have built theories that predict experimental outcomes to 10 decimal places. We have detected ripples in spacetime from colliding black holes a billion light years away and matched those signals to equations written down a century ago. We have mapped the behavior of subatomic particles with an accuracy that makes most other scientific achievements look like rough estimates. By any reasonable measure, physics works. It works extraordinarily well, and it is broken. Here is the thing that should stop you. We have two theories sitting at the center of modern physics. One describes gravity, the large-scale shape of the cosmos, the motion of planets, the behavior of light near massive objects. The other describes everything else at the subatomic level, the particles, the forces, the quantum behavior that underlies all of chemistry and biology and matter itself. Both are tested beyond any reasonable doubt. Both produce predictions of staggering precision, and they are fundamentally incompatible, not slightly off from each other, not in need of minor adjustment, incompatible at the level of what they say reality is made of and how it behaves. That is where this story starts. But it does not stop there, because the incompatibility between those two theories is only the most technically defined version of the problem. Pull back further, and the picture gets stranger. Roughly 95% of the universe, by current best estimates, is invisible to us. Not distant, not difficult to reach, invisible. It does not emit light, does not absorb light, does not interact with any instrument we have ever built in any way we can directly measure. We know it is there because of what it does to the 5% we can see. We have named it. We have mapped its gravitational effects. We have not identified what it actually is. And then there is the question of why anything exists at all. The physics of the early universe says matter and antimatter should have been produced in equal quantities. Equal quantities annihilate each other completely. If that symmetry held, the universe would have destroyed itself in the first fraction of a second, leaving nothing. No galaxies, no stars, no atoms, no biology, no one to ask the question. Something broke that symmetry. Something produced a slight excess of matter, one part in roughly a billion, and everything that has ever existed is the residue of that imbalance. We do not know what caused it. The best theory we have predicts an asymmetry orders of magnitude too small to account for what we observe. And then there is time and consciousness. Physics cannot tell you why time moves in one direction. The equations are symmetric. They work equally well in both directions. The irreversibility you experience every moment of your life does not appear in the fundamental laws. Consciousness does not appear in them either. We have no physical theory of why there is something it is like to be alive and aware, why any arrangement of matter produces subjective experience rather than just processing in the dark. These are not edge cases. These are not open questions parked at the margins while the main work proceeds. They are the main work. And the field proceeds anyway, the way you might keep painting walls while ignoring the crack running up the foundation. That is not a philosophical quibble or a footnote in a textbook. That is the ground opening up under the entire structure of modern physics. General relativity is not approximately correct. It is correct to a precision that makes most other scientific achievements look like rough estimates. In 2015, two black holes collided more than a billion light years from Earth. The collision sent ripples through the fabric of space-time itself. Those ripples, gravitational waves, traveled for over a billion years, arrived at Earth, and moved the mirrors of the LIGO detector by a distance smaller than 1/10,000th the width of a proton. LIGO found them. The signal matched Einstein's predictions at a confidence level of more than 20 sigma. That is not a successful experiment. That is one of the most precise confirmations of any physical theory in history. Now look at the other side. The standard model of particle physics predicted the magnetic moment of the electron, a number describing how the electron responds to a magnetic field, to 10 decimal places. Experiments confirmed it to 10 decimal places. 10. If you were trying to measure the distance between New York and Los Angeles, and your theory was accurate to the width of a human hair, that is roughly the level of precision involved. These are not working theories in the sense of useful approximations. They are the closest thing to exact descriptions of physical reality that science has ever produced. Here is the problem. They are mutually incompatible, not in some minor technical sense that future mathematics will tidy up. Fundamentally, at the level of what they each say reality actually is. General relativity describes gravity as the curvature of spacetime. Mass tells spacetime how to curve, spacetime tells mass how to move. The geometry is smooth, continuous, and deterministic. Given the positions and velocities of everything in a system, the equations tell you exactly what will happen. There is no randomness, there is no uncertainty, there is no probability. The universe in general relativity is a single continuous surface bending in response to mass, and the future is written in the geometry of the present. Quantum field theory describes everything else: the electromagnetic force, the weak nuclear force, the strong nuclear force, every particle that has ever been detected in a collider. In this description, nothing is smooth, nothing is continuous. Everything operates through discrete exchanges. Particles interact by passing other particles between them. Position and momentum cannot both be known precisely, not because our instruments are limited, but because at the fundamental level the universe genuinely does not have both values simultaneously. Probability is not a placeholder for ignorance, it is built into the structure of reality. These two descriptions have never failed an experiment. They have also never been successfully combined into a single coherent framework. Every attempt produces the same result. The mathematics breaks. Before you can understand why this matters, you need to understand what scale the breakdown happens at. The Planck length, 10 to the negative 35 meters, is the scale at which quantum effects on spacetime become impossible to ignore. At that scale, the smooth, continuous geometry of general relativity is expected to dissolve into something violently chaotic. Space itself should be foaming and fluctuating and fundamentally uncertain. But general relativity has no room for uncertainty, and quantum mechanics has no framework for curved spacetime. At the Planck length, both theories reach the edge of their domain and stop working simultaneously at the exact scale where you need at least one of them to work. What does that look like in practice? Consider a black hole. General relativity describes a black hole with complete mathematical precision right up to its center. At the center sits a singularity, a point where the density becomes infinite and the curvature of spacetime becomes infinite. Physically, what does that mean? It means the equations have broken down. Infinity in a physics equation is not a measurement, it is a signal. It tells you that the theory has been pushed past the boundary of its validity, that something is happening which the framework cannot describe. The singularity is not a prediction of what exists at the center of a black hole. It is general relativity admitting that it cannot tell you. Now apply quantum mechanics to the same situation. A photon near the event horizon of a black hole exists in a region of extreme spacetime curvature. To describe it accurately, you need general relativity for the curvature and quantum field theory for the photon. You apply both simultaneously. The calculation returns infinities that cannot be removed, not the manageable infinities that quantum electrodynamics learned to absorb through renormalization, infinities that proliferate without bound, that make the result meaningless rather than approximate. The two most powerful tools in physics, applied together to the same object, produce mathematical nonsense. The Big Bang has the same structure. Run general relativity backward to the first moments of the universe and you reach another singularity: infinite density, infinite temperature, the equations collapsing into the same confession they make at the center of a black hole. Quantum mechanics should dominate at those scales and energies. But there is no accepted quantum description of that moment. There is no theory that tells you what happened at or before the Planck time in the early universe. What this means is specific and serious. The two events we most want to understand, the birth of the universe and the interior of black holes, are precisely the events where our best theories fail completely, not approximately, not around the edges, at the center of the question. Every infinity the equations produce is a confession. At the moments that matter most, we are completely blind. In the 1960s and 1970s, An astronomer named Vera Rubin looked at how galaxies spin and found something that should have stopped physics in its tracks. She was measuring rotation curves. The idea is straightforward. Take a spiral galaxy, measure how fast stars are orbiting at different distances from the center, and plot the results. Basic physics, Newtonian, then Einsteinian, makes a clear prediction about what you should find. Stars near the center, where most of the visible mass is concentrated, should orbit fast. Stars out at the edges, far from the gravitational bulk of the galaxy, should orbit much more slowly. Mercury moves faster than Neptune. The inner planets are pulled harder. The outer planets drift. That is what gravity does at a distance. It weakens, and orbital speeds fall accordingly. Rubin's curves did not fall. Stars at the outer edges of spiral galaxies were moving at roughly the same speed as stars near the center, not slightly faster than expected, not marginally off. The same speed. Across galaxy after galaxy, the rotation curve stayed flat where every prediction said it should drop. That is not a subtle anomaly requiring careful statistical analysis to detect. That is a screaming contradiction sitting in the open, visible in the data, impossible to paper over with error bars. Here is the only explanation that works. There is mass out there that we cannot see, not a little mass. Enormous quantities of it, distributed in a vast halo extending far beyond the visible disk of the galaxy, providing the gravitational pull that keeps those outer stars moving at the speeds Rubin recorded. Remove the invisible mass and the galaxy should shed its outer stars like water flying off a spinning wheel. The visible matter is not enough. It is not close to enough. When you add up the invisible mass required to produce the rotation curves Rubin and her colleagues measured across galaxy after galaxy, you arrive at a ratio. Galaxies contain roughly 6 times more of this invisible matter than all the visible matter, every star, every gas cloud, every detectable object combined. 6 to 1. That is not a small correction to an otherwise accurate picture. That is the picture being wrong by a factor of 6 about what most of reality is made of. Scientists named it dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at any wavelength. Every telescope ever built, operating across every band of the spectrum from radio waves to gamma rays, sees nothing where the dark matter should be. We infer it entirely from what gravity does in its presence. It is there the way a wind is there, not visible, but the evidence of its force is everywhere. Now hold that problem in your head and add a second one. In the 1990s, 2 independent teams of astronomers set out to measure how much the universe's expansion was slowing down. This was not a radical question. After the Big Bang, the universe began expanding. Gravity, everyone assumed, was gradually pulling it back, decelerating the expansion the way a ball thrown upward decelerates in flight. The question was simply, how much? Was there enough matter to eventually halt the expansion and collapse everything back? Or would the expansion continue forever, just at a decreasing rate? Both teams used Type 1a supernovae as measuring tools. These particular explosions have a consistent peak brightness, which makes them reliable distance markers. Measure the brightness, calculate the distance. Measure the redshift, calculate the recession velocity. Compare distances and velocities across cosmic time and read off the deceleration rate. The method was sound. The data came back. The expansion was not decelerating, it was accelerating. The universe is not slowing down. It is flying apart faster every year. Whatever is driving this acceleration acts in direct opposition to gravity. It pushes outward rather than pulling inward, and it does so across the entire fabric of space. Both teams found the same result independently, which rules out systematic error. The discovery earned the Nobel Prize in Physics in 2011, and the thing driving it has no physical description beyond the fact of its existence. An astrophysicist named Michael Turner coined the term dark energy in 1998. He named it that because the name communicated exactly what they knew, which was almost nothing. Something in the structure of space itself is producing this acceleration. It might be a property of empty space, what Einstein called the cosmological constant, a baseline energy density that the vacuum of space carries at every point. It might be a new field, something never detected, with properties unlike anything in the standard model. We have named the phenomenon. We have not explained it. Here is the full accounting of what that leaves us with. Dark matter makes up roughly 27% of the universe's total energy content. Dark energy makes up approximately 68%. Ordinary matter, every particle described by the Standard Model, every atom in every star and planet and human body, every photon ever detected by any instrument, accounts for about 5%. 5%. Everything physics has ever described, every experiment ever run, every equation ever written down, every theory ever verified, all of it applies to 5% of what is actually out there. The Standard Model is a masterwork of human intellect that describes a small fraction of a fraction of the universe's content. General relativity bends and curves a space-time that is 95% filled with things it cannot account for. Dark energy is not even stable in the equations without a term Einstein himself called his greatest blunder and later removed. And yet, when you read a physics textbook, you read about a field that has produced a remarkably complete picture of reality. That framing is only possible if you agree not to ask what the other 95% is. We built the entire framework of modern physics on 5% of what's actually there, and we called that a complete description of the universe. The bullet cluster is one of the clearest images in modern astrophysics, and it shows something that has no explanation. Two galaxy clusters collided. When they did, the ordinary matter, the gas, the plasma, all the visible material, slowed down. It collided with itself. It heated up. It glowed in X-ray. You can see exactly where it ended up. Then astronomers mapped the gravitational lensing around the collision. Lensing is the bending of light from background objects caused by mass sitting in the foreground. It does not care what the mass is made of. It does not care whether the mass emits light. It responds to gravity, and gravity responds to mass, and that is all. What the lensing showed was that the majority of the mass in both clusters passed straight through the collision and continued moving. It did not slow down. It did not interact. It passed through billions of tons of plasma as if nothing was there. The mass and the visible matter had separated. You could see them separately. The gas was here. The mass was there. That is not a theoretical prediction dressed up as evidence. That is a direct observation of dark matter behaving exactly the way the model says it should. The bullet cluster is, in the view of most physicists, the single most compelling direct evidence for dark matter's existence. And here is the problem. We can see what it does. We have no idea what it is. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at any wavelength. Every instrument we have built for observing the universe, optical telescopes, radio arrays, X-ray observatories, gamma-ray detectors, works by collecting electromagnetic radiation. Dark matter produces none. It absorbs none. It is completely transparent to the entire electromagnetic spectrum. The only thing it does is pull, gravitationally, and that pull is everywhere, around every galaxy, in every galaxy cluster, threaded through the large-scale structure of the universe itself. The distribution of dark matter shaped how the first galaxies formed. It determined where matter clumped together in the early universe. The universe we live in, its structure, its web of filaments and voids, looks the way it does because dark matter organized it, and we do not know what dark matter is made of. For 30 years, the leading candidate was something called a WIMP, weakly interacting massive particle. The name tells you everything about the hypothesis. A particle with mass, enough mass to account for the gravitational effects, but one that interacts only through gravity and the weak nuclear force, not electromagnetism. That would explain why it is invisible. The weak force operates only at subatomic distances, so a WIMP passing through ordinary matter would almost never interact with it. Almost, not quite never. And that almost was what made WIMPs testable. If dark matter is made of WIMPs, then occasionally, very rarely, one should collide with an atomic nucleus. The collision would be detectable, barely, but detectable. So physicists built detectors. They went underground to shield out cosmic rays and background radiation. They cooled instruments to temperatures near absolute zero to reduce thermal noise. They built tanks filled with liquid xenon or germanium crystals, waiting for a single dark matter particle to strike a nucleus and produce a faint recoil signal. The LUX experiment. Xenon 1T Pandax LZ. These are not casual projects. They represent decades of engineering and hundreds of millions of dollars and careers built around a single question. What does a WIMP interaction look like? The answer, so far, is this: nothing. Every experiment has returned a null result, and the null results are not ambiguous. Each generation of detector has been more sensitive than the last by significant factors. The parameter space, the range of masses and interaction strengths where WIMPs could be hiding, has been mapped and eliminated in large sections. The region where WIMPs were most theoretically favored is now ruled out, not weakly constrained, ruled out. The signal is not there at the sensitivity where theory said it should be. What happens when the leading candidate for the most abundant form of matter in the universe is progressively eliminated by the very experiments designed to find it? The field adjusts. It proposes that WIMPs might be lighter than expected or heavier. It builds more sensitive detectors. It continues. But here is what the null results actually mean. Either dark matter is not made of WIMPs, which leaves the question completely open, or it interacts so weakly that we are nowhere near the sensitivity required to detect it, which means we may be looking for the wrong thing in the right place for a very long time. Neither option is comfortable. We have confirmed that dark matter is real. The bullet cluster alone makes denial unreasonable. We have confirmed that it has mass. We have confirmed that it is everywhere. We cannot find a single particle of it with any instrument we have built. That is not a gap at the edge of the problem. That is the center of the problem. And it has not moved in 30 years of increasingly sensitive experiments have found nothing, and each null result tightens the walls of the room we are trapped in. The honest answer to why there is something rather than nothing is that we do not know, and that is not a philosophical dodge. It is a specific, measurable gap in the most fundamental theory we have. Here is what the physics requires. At the moment of the Big Bang, matter and antimatter should have been produced in equal quantities. That is not an assumption. It follows from the symmetry laws built into the Standard Model. Equal parts, opposite charge, identical in every measurable way except sign. And when matter and antimatter meet, they do not coexist, they annihilate completely. A particle and its antiparticle collide and both disappear, converted entirely into radiation. If the universe began with perfect symmetry, that process runs to completion. Every particle finds its partner. Every annihilation produces light. What remains is a universe of radiation and nothing else. No atoms, no hydrogen, no stars, no planets, no chemistry, no biology, no one to notice. We are here. That means the symmetry broke. Somewhere in the first fraction of a second, the universe produced slightly more matter than antimatter. Not much more. Roughly one extra matter particle for every billion matter-antimatter pairs. The annihilation happened anyway, a billion particles of matter meeting a billion particles of antimatter, wiping each other out completely. But that one leftover particle had no partner. It survived. Everything you have ever seen, every galaxy measured, every atom in your body, is the accumulated residue of those survivors. The entire observable universe is built from the wreckage of an imbalance so small it barely registers as a rounding error. That is not poetic language. That is the actual accounting. Now here is the problem. The Standard Model does allow for a difference in how matter and antimatter behave. It is called CP violation, a subtle asymmetry in certain particle decay processes where matter and antimatter do not behave as perfect mirrors of each other. Physicists discovered it experimentally in the 1960s. It is real, it is measured, and the amount of CP violation the Standard Model predicts is orders of magnitude too small to explain the imbalance we observe. Not slightly too small, not close. The gap between what the Standard Model produces and what the universe actually did is enormous. Something else drove that asymmetry. Something outside the current framework, some mechanism we have not identified, tipped the balance in the first instant and left everything we will ever know as its consequence. What does that tell you? It tells you that the most fundamental question you can ask, why does anything exist at all, has a specific physical answer, and we do not have it. This is not a question physics has declined to address. Physicists have been working on it for decades. The mechanisms proposed have names: leptogenesis, electroweak baryogenesis, beyond Standard Model CP violation. The experiments designed to test them are real and serious. The Dune experiment will begin collecting data in 2026. It will fire a beam of neutrinos and antineutrinos from Fermilab across 800 miles of Earth to a detector in South Dakota, looking for differences in how they behave. Neutrinos are a candidate. If they violate CP symmetry at a large enough scale, that could point toward the mechanism that tipped the balance at the Big Bang. But that answer is not in yet. Before you can understand why this gap matters, you need to sit with the scale of what it represents. We are not missing a correction term. We are missing the explanation for why the universe is populated rather than empty. Every star that has ever burned, every planet that formed around one, every chemical reaction that built the first organic molecules, every living thing that has ever existed, all of it traces back to that 1 in a billion excess. Remove it, and the universe is featureless radiation cooling toward equilibrium with nothing inside it. The asymmetry is the universe, and we cannot explain it. My view on this matter is clear. When the gap in an explanation is that large, when the thing left unexplained is the existence of everything, the honest scientific response is to say the framework is incomplete in a fundamental way, not at its edges, but at its foundation. The Standard Model is the most precisely tested theory ever produced. It is also missing the answer to the most basic question the universe poses. Those two facts are both true simultaneously, and the field has largely continued working within the framework anyway. That is not criticism. The framework works, but it does not work here, at exactly the moment it would matter most. Everything you can see, everything that has ever existed, is the debris from a 1 in a billion accident that physics cannot explain. There is a specific moment when the two best theories in physics meet each other, and what happens at that moment is not a compromise or a blend. It is a complete mathematical breakdown. Before you can understand why that matters, you need to understand one thing about how quantum field theory actually works. Just one. The rest follows from it. When physicists first tried to calculate the behavior of electrons using quantum mechanics, they kept getting the same result: infinity. The equations returned infinite values for measurable physical quantities. That is not a small problem. That is the theory telling you it does not know what it is doing. The solution physicists developed is called renormalization. It is a procedure, a mathematical technique, for absorbing those infinities into the definitions of physical constants, the mass of an electron, its charge, and then moving forward with finite, testable predictions. It is not intuitively satisfying. Some physicists, including Dirac, called it a trick, but it works. Renormalization makes quantum electrodynamics the most precisely verified theory in the history of science. It works for the weak force. It works for the strong force. The Standard Model is built entirely on it. And then you try to apply it to gravity. The infinities come back. Not one infinity, infinitely many. Every time you try to absorb one, two more appear. The procedure that saves every other force in physics fails completely when gravity is introduced. The equations for quantum gravity are not renormalizable. That is not a technical footnote. That is the wall. Here is what that looks like in practice. Say you want to calculate something specific: a photon falling toward a black hole. A simple enough physical scenario: a particle of light in an intense gravitational field. To describe this correctly, you need general relativity because the gravitational field is extreme. You also need quantum mechanics because a photon is a quantum object. Both theories are required simultaneously, so you apply both. What comes out is not approximately wrong. What comes out is mathematical nonsense. The equations return infinity for quantities that are supposed to have definite measurable values, not very large numbers, infinity, which is the theory's way of saying it cannot describe this situation at all. Not poorly, not approximately, not at all. And that specific situation, a quantum particle in extreme gravity, is not exotic. It describes the inside of every black hole. It describes the first moments after the Big Bang. These are not edge cases. These are the most consequential events in the history of the universe, and we have no physics that covers them. Every black hole singularity in the known universe sits behind a mathematical wall our best tools cannot penetrate. The Big Bang itself sits behind the same wall. We can trace the universe backward in time with extraordinary precision, back to fractions of a second after the beginning, and then the equations break down and return infinity, and we are blind. That is the situation, not nearly solved, blind. Here is the part that should stop you. Physicists have known this for nearly a century. The incompatibility between general relativity and quantum mechanics is not a new discovery. It is older than the moon landings. It is older than the transistor. And in that time, two serious research programs have emerged to solve it. Both have attracted extraordinary mathematical talent. Both have produced genuinely beautiful work. Neither has produced a testable prediction. The first is string theory. The proposal is this: the fundamental constituents of matter are not point particles. They are one-dimensional objects, strings, vibrating in 10 or 11 dimensions. The vibrational modes of a string determine what particle it appears to be. Change the vibration, change the particle. And gravity emerges naturally from this picture. One particular vibrational mode of a string behaves exactly like a graviton, the quantum carrier of gravity that standard quantum mechanics cannot accommodate. The incompatibility dissolves. The mathematics is consistent. This is genuinely remarkable. String theory also produced the ADS/CFT correspondence, a discovery that has turned out to be useful in ways that go far beyond quantum gravity, touching condensed matter physics and the study of strongly coupled quantum systems. But the extra dimensions required by string theory have never been observed. The supersymmetric partner particles the theory predicts, one for every known particle, have not appeared despite the Large Hadron Collider reaching energies where they were expected to show up. The theory does not uniquely predict the universe we live in. It predicts an almost incomprehensible number of possible universes. The mathematics is extraordinary. The contact with physical reality is, so far, absent. The second approach is loop quantum gravity. Where string theory keeps spacetime smooth and changes what matter is, loop quantum gravity changes spacetime itself. Space, in this picture, is not continuous. It comes in discrete minimum chunks, the way matter comes in atoms. There is a smallest possible distance, the Planck length, below which the concept of space breaks down. Time is also discrete. The smooth spacetime of general relativity is an approximation, the same way a smooth surface is an approximation of the discrete atomic structure beneath it. This also resolves the incompatibility in a mathematically consistent way. It also makes predictions about the behavior of spacetime at the Planck scale, about modifications to the dispersion of light over cosmological distances, and those predictions are currently untestable. The Planck length is 10 to the negative 35 meters. Probing that scale directly would require a particle accelerator larger than the observable universe. Heisenberg, near the end of his life, allegedly said he would ask God two questions: why relativity and why turbulence? And he expected an answer only to the first. The quantum gravity problem is the turbulence problem elevated to a different scale entirely. Not the behavior of water in a pipe, but the behavior of space and time themselves at the smallest conceivable scale. The equations we would need to solve are not merely difficult. They may be, with any technology we can foresee building, permanently beyond experimental reach. We have two candidates for the theory that fixes this, and neither has produced a single prediction we can test with any instrument that currently exists or could be built in any conceivable near future. String theory has attracted more raw mathematical talent over the past half-century than almost any other research program in the history of science. That is not an exaggeration. It is a documented pattern of recruitment. Graduate students with the highest aptitude, the strongest mathematical instincts, the most promising early careers, generation after generation, they went into string theory. The brightest people in the room chose this problem, and that fact is worth holding on to as you hear what follows. Here is what string theory actually proposes. Instead of point particles, the electrons, quarks, photons of the standard model, the fundamental constituents of reality are tiny one-dimensional strings, unimaginably small, far below anything any instrument has ever detected or could detect. These strings vibrate. Different vibrational modes correspond to different particles. One particular mode produces a particle with the properties of a graviton, the hypothetical carrier of gravity. That is the moment the whole program becomes significant. Gravity falls out of the mathematics naturally, without being inserted by hand. For the first time in the history of physics, a framework existed that seemed to contain both quantum mechanics and gravity within the same structure. That is not nothing. That is, on paper, exactly what the field had been looking for. The mathematics that followed was extraordinary, genuinely. The discovery of the ADS/CFT correspondence in 1997, a precise mathematical equivalence between a theory of gravity in a higher dimensional space and a quantum field theory on its boundary, turned out to describe systems in condensed matter physics that had nothing obvious to do with string theory. Physicists studying strange metals and superconductors started using string theory tools because those tools produced results that worked. That is a real contribution. That is the mathematics telling you something true about the universe, even if you are not sure exactly what. But here is the core problem. The strings require extra dimensions, not 1 or 2, 10 or 11, depending on which version of the theory you are working in. The 6 or 7 extra dimensions beyond the familiar 4 are curled up at scales so small they are undetectable. This is not a minor technical assumption, it is the load-bearing wall of the entire structure, and there is no observational evidence that those dimensions exist. None. Not a signal, not an anomaly, not a residual effect. The dimensions the theory requires are, by design, forever hidden from any instrument we can build. Then there is supersymmetry. The string framework predicts that every known particle has a supersymmetric partner, a heavier twin with different quantum properties. These partner particles were expected to show up at the Large Hadron Collider. The LHC reached energies where supersymmetric particles were predicted to appear by the internal logic of the theory. The experiments ran, the detectors looked, the partners were not there. That is not ambiguous data. That is a clean null result at energies the theory itself specified as the relevant range, and this is what should fundamentally shake your confidence in the framework. The mathematics of string theory does not predict a single universe. It predicts approximately 10 to the power of 500 possible universes, each with different physical constants, different particle masses, different values for gravity and electromagnetism and every other parameter. Write out that number and it is a 1 followed by 500 zeros. The number of atoms in the observable universe is roughly 10 to the 80. The string landscape is incomprehensibly larger than that. What this means, practically, is that the theory does not tell you which universe you should be in. It tells you that almost any universe is possible. A theory that permits virtually any outcome predicts nothing. Some physicists looked at this and reached for the anthropic principle. We observe the constants we observe because we can only exist in a universe where those constants permit life. Observers can only find themselves in universes compatible with observers. That is the argument. And the argument is logically valid. It is also not testable. You cannot design an experiment to confirm or falsify it. You cannot make a prediction from it that distinguishes it from any other framework. That is not physics. That is a position on why physics cannot answer the question. What does that tell you about where the program ended up? 50 years ago, string theory began as an attempt to unify all forces and explain why the universe has the structure it has. The mathematics led step by step to a framework that predicts 10 to the 500 possible structures. The response to that, from within the program, was to say that we live in this particular structure because we could not live in the others. That is the logical terminus of 50 years of work by some of the most capable mathematical minds the field has ever produced. The question is not whether string theory produced beautiful mathematics. It did. The question is whether beautiful mathematics constitutes a description of physical reality in the absence of any confirmed contact with experiment. There is a word for that question, and it is a serious one. It is not a word the field has been comfortable applying to itself. The professional investment is too large, the careers too deep, the institutional momentum too strong. That calculation is not unique to string theory. But the scale of it here is unlike anything else in the history of the discipline. After 50 years, the most mathematically sophisticated theory ever produced by physics has not made a single confirmed prediction about the physical universe, and the field has continued anyway. Mary knows everything there is to know about color, every wavelength, every neuron, every chemical signal that fires when a human eye processes red, and she has never once seen it. That is the setup for a thought experiment that has been sitting in philosophy of mind for 40 years, and it has not been answered. Mary is a scientist raised entirely in a black and white room. She learns everything physics and neuroscience can tell her about color vision, every wavelength, every cone cell in the retina, every firing pattern in the visual cortex when a human eye encounters red light at 700 nanometers. She knows the complete physical story. Then she walks out of the room. She sees red. Does she learn something new? And if yes, then there are facts about conscious experience that the complete physical description of the world does not capture. That is not a small gap. That is physics hitting a wall it did not know was there. Here is why this problem is different from everything else in this script. Dark matter is a gap in our inventory of the universe. Quantum gravity is a gap in our mathematical tools. The hard problem of consciousness is a gap in what the tools can even address. It is not that we have the wrong equations. It is that we are not sure equations are the right language at all. The easy problems of consciousness are genuinely difficult. Explaining how the brain integrates sensory information, controls attention, stores memory, generates behavior. None of that is simple. But those problems are tractable in principle. They are engineering problems. You map the mechanisms, trace the signals, build the model. Given enough time and enough data, you close the gap. The hard problem is different in kind, not just degree. It asks why any physical mechanism produces subjective experience at all. Why is there something it is like to be you? Why does the processing feel like anything? A system could in principle take in information, integrate it, respond to it, report on it, and do all of that in complete darkness with no inner experience whatsoever. The question is why that is not what happens. Here is the tool philosophers use to make that precise. A philosophical zombie is a being physically identical to you in every way. Same neurons, same chemistry, same brain states, same behavior. It responds to pain, reports being happy, claims to feel the warmth of sunlight. But there is nothing it is like to be it. No inner experience, no light on inside. The question is whether that is conceivable. Most people who think carefully about it conclude that it is. And if it is conceivable, then consciousness is not entailed by the physical facts. You can have all the physics and none of the experience, which means we have no theory of why experience shows up at all because the physical description is complete without it. What does that mean for physics? It means the map is missing an entire continent, not a country, a continent. The subjective quality of experience, what philosophers call qualia, does not appear anywhere in the equations of the standard model. It does not appear in general relativity. It does not appear in any physical theory currently on the table. We have no variable for it, no unit of measurement, no handle. The experience of seeing red is as real as the wavelength that produces it, and one of those things has a complete physical description and the other does not. Some responses to this are worth taking seriously. Panpsychism proposes that consciousness is not something that emerges from complex physical systems, but something that is fundamental to reality at the lowest level. The way mass and charge are basic properties, consciousness is a basic property, present in some form everywhere, amplified and organized by complex structures like brains. This is not obviously crazy. It solves the emergence problem by refusing to make consciousness emergent. Whether it is true is a different question, and we currently have no way to test it. Roger Penrose, working with anesthesiologist Stuart Hameroff, proposed that consciousness involves quantum processes in protein structures called microtubules inside neurons. The argument is that classical computation cannot account for certain features of conscious thought, and quantum effects in the brain could. The proposal is genuinely controversial. Most neuroscientists are skeptical. But the fact that a physicist of Penrose's caliber directed significant effort here tells you something about how seriously the problem is taken by people who understand what the alternatives look like. And then there is artificial intelligence, which has made this urgent in a way it was not a decade ago. We are building systems that report experience, claim inner states, respond with apparent sensitivity to emotional context. The hard problem becomes immediately practical. If we cannot explain why physical processes in biological brains produce experience, we have no principled way to determine whether physical processes in silicon produce it too. We are making that judgment on behavioral evidence alone, which is exactly the evidence the philosophical zombie thought experiment tells us is insufficient. We are running the experiment before we understand the phenomenon. The hard problem has been known as a formal problem since David Chalmers named it in 1995. Before that, it was implicit in decades of philosophy of mind. Before that, it was implicit in every serious attempt to explain what the mind is. The field has not made decisive progress on it, not because the people working on it are not capable, because the problem may require a framework that does not yet exist. The only instruments we have for studying consciousness are conscious, and we have no idea what that means. Run any equation in fundamental physics backward in time and it works perfectly. The laws of physics do not know which direction time is supposed to go. That is not a poetic exaggeration. It is a precise technical statement. Take Newton's equations, Maxwell's equations, the equations of quantum mechanics, the equations of general relativity, run them forward, run them backward. The mathematics does not distinguish. A film of two billiard balls colliding is physically valid in either direction. The equations governing that collision work identically whether time moves forward or backward. There is no arrow written into the laws. There is no preferred direction. Past and future are, at the level of fundamental physics, equally legitimate. So here is the question. Why does a shattered glass not reassemble itself off the floor? Nothing in the laws prohibits it. Every particle interaction that scattered that glass into fragments could, in principle, reverse. The fragments could converge, rise, reform into a glass on the table. The equations allow it. It never happens. You have never seen it happen. You will never see it happen. And the fact that you know that with absolute certainty, while the equations remain completely silent on the matter, is the arrow of time problem. The standard answer involves thermodynamics, entropy. Systems evolve towards states of higher disorder because there are vastly more disordered arrangements than ordered ones. A glass of hot water left in a cold room will cool down, not heat up, because the equilibrium state has far more ways to be disordered than ordered. The forward direction of time is the direction of increasing entropy. That is the answer in the textbooks, and it is not wrong exactly, but it pushes the problem back rather than solving it. Here is why. If entropy increases over time, then entropy was lower in the past. Follow that logic back far enough and you reach the Big Bang, which had to be in an extraordinarily low entropy state. The entire structure of cosmic history, every star that formed, every galaxy that organized, every creature that metabolized, every thought that was ever thought, depends on that initial condition. The universe started in a highly ordered state, and everything since has been the gradual unfolding of that order into disorder. That direction, from low entropy to high, is what we experience as time passing. But why did the Big Bang start with such low entropy? That question has no answer in the standard model. It has no answer in general relativity. It is simply an initial condition that we observe and cannot explain. We have replaced the question of why time has a direction with the question of why the universe started in the particular configuration it did. That is not a solution. It is a restatement. What does that tell you? It tells you that the arrow of time is not a feature of the laws of physics. It is a feature of the universe's history. The laws are time-symmetric. The history is not. And we have no deeper theory that explains why the history began the way it did. Now sit with what that actually means. Every experience you have of time, memory, anticipation, cause preceding effect, the sense that the past is fixed and the future is open, every one of those experiences rests on that unexplained initial condition. Causality itself, the principle that causes come before effects, is not guaranteed by the fundamental equations. It is an emergent property of the universe having started in a low entropy state. If that initial condition were different, the direction of causality could be different, or there might be no preferred direction at all. This is where the problem becomes more than a physics problem. If the equations are time-symmetric, then the distinction between past and future is not fundamental to reality. It is something the universe does, not something the universe is, and we have no account of why it does it. We experience causality as the most basic feature of how things work. Something happens, then something else happens because of it. That sequence feels like it is written into the nature of reality. It is not written into any equation we have. The thing you are most certain of, that the past is fixed and the future is open, appears nowhere in the equations that are supposed to describe everything. Change the strength of gravity by a tiny fraction and stars never form. They either collapse immediately or scatter their material before nuclear fusion can ignite. That is not a metaphor. That is the actual calculation. Physicists have run the numbers on what happens when you adjust the fundamental constants of the universe, and the answer is always the same. Move them slightly, and everything falls apart. Not metaphorically apart, literally apart. No stars, no heavy elements, no chemistry, no planets, no biology, no one asking the question. The universe as we know it exists inside a set of values so precisely arranged that the arrangement itself demands an explanation. We do not have one. Here is what we are actually talking about. The universe runs on constants, numbers baked into the fabric of reality that do not change and cannot be derived from anything deeper. The strength of gravity, the mass of the electron, the cosmological constant, which is the value associated with dark energy, the charge on a proton, the fine structure constant governing electromagnetic interactions. These numbers are what they are. Physics measures them. Physics does not explain them. And when you ask what happens if they were slightly different, the answer is almost always catastrophic. Change the strong nuclear force by a few percent in either direction, and stars cannot fuse hydrogen into the heavier elements that chemistry requires. Carbon, oxygen, iron, gone. The periodic table stops at helium. Nothing complex ever forms. Adjust the cosmological constant upward by even a small fraction, and the universe expands so rapidly that matter never has time to clump into galaxies. Adjust it downward, and the universe collapses back on itself before a single star ignites. The window inside which the constants permit a complex universe is extraordinarily narrow, and we sit precisely inside it. This is the fine-tuning problem, not a paradox in the philosophical sense. A specific, measurable, uncomfortable fact about the structure of reality. The constants are not obviously necessary. They are not derived from a deeper equation. They sit in the laws of physics the way unexplained numbers sit in an equation, present, precise, unaccounted for. And the precision required is not modest. The cosmological constant, for instance, appears to be fine-tuned to something on the order of 1 part in 10 to the power of 120. That is not a rough estimate. That is the number the physics produces. A deviation that small in any other direction and we do not exist. Now here is where the field stands. 3 explanations have been offered. None of them are satisfying, and it is worth being honest about why. The first is coincidence. We simply happen to live in a universe with the right constants. This is not an explanation. It restates the problem in different words. Saying the constants are what they are because they are what they are is not a scientific account of anything. It is an admission that no account exists. The second is the multiverse. If string theory is correct, there may be something on the order of 10 to the power of 500 distinct universes, each with different values for the fundamental constants. In that case, we necessarily find ourselves in one of the rare universes compatible with our existence. We could not find ourselves anywhere else. This is called the anthropic principle, and it has a certain logic to it. But here is my position on that. It is unfalsifiable. We cannot observe other universes. We cannot test whether they exist. A theory that explains everything without the possibility of being wrong is not science in any recognizable sense. It is a mathematical framework dressed as an answer. The third explanation is that a deeper principle exists. Some physics we have not found, some more fundamental equation whose solution makes these particular values necessary rather than accidental. This would be a real answer. It would mean the fine-tuning is not tuning at all, just a consequence of something deeper we have not seen yet. That is the answer physics is built to find. We do not have it. Nothing in the standard model produces the constants. Nothing in general relativity explains them. String theory was supposed to derive them and produce 10 to the power of 500 possibilities instead. The universe has handed us a specific question in the form of numbers. Why these values? Why this window? Why anything complex at all? And after decades of serious effort, we are still standing in front of that question with nothing definitive to say. 3 explanations exist for why the constants have the values that allow us to exist, and none of them are satisfying, and none of them are testable, and the question just sits there. Quantum mechanics is the most precisely verified theory in the history of science, and nobody agrees on what it means. Not approximately, not in the details. On the most basic question you can ask about a physical theory, what is it actually describing? Physicists have been in genuine disagreement for 100 years. That is not a footnote. That is a problem sitting at the center of the most foundational tool in modern science. Here is what the theory says, precisely. A quantum system, an electron, a photon, any particle, does not have a definite position, spin, or momentum before you measure it. It exists in a superposition, a weighted combination of all possible states at once. When you measure it, the superposition collapses. You get one outcome. The math tells you the probability of each possible outcome with extraordinary precision, and the predictions match experiment to a degree that embarrasses every other theory in physics. So the formalism works, the predictions are correct, and the question of what is actually happening in physical reality between measurements has no agreed answer. None. After a century of some of the sharpest minds ever to work in science, the interpretation remains open. Here is the dark part. This is not a question physicists expect to resolve with a better experiment next year. The disagreement is not empirical, it is deeper than that. The competing interpretations make the same predictions. You cannot distinguish between them by measuring anything. That means the standard tools of science, observation, falsification, experimental elimination, cannot settle this. The question of what quantum mechanics means is, in a precise sense, beyond the current reach of experimental physics. The oldest interpretation is called Copenhagen. Niels Bohr and Werner Heisenberg formalized it in the 1920s, and it dominated for decades. The Copenhagen position is essentially this. The wave function is a tool for calculating probabilities, not a description of physical reality. Do not ask what the system is doing before measurement. That question has no answer. Use the formalism, get the predictions, stop there. This is operationally successful. It produced the transistor and the laser and every piece of quantum technology you interact with daily. It is also philosophically bankrupt because it builds the act of measurement into the foundations of physics without ever explaining what a measurement is or what causes the collapse or where the boundary sits between the quantum system and the measuring device. The many worlds interpretation eliminates that boundary entirely. Hugh Everett proposed it in 1957, and the idea is radical in the most literal sense. The wave function never collapses. Every quantum event produces a branching. Every possible outcome happens in some branch of a universal wave function that never stops splitting. When you measure an electron's spin and get up, there is a branch of the universe where you measured down. Both branches are real. Both versions of you continue forward. What you experience as a single definite outcome is just your particular branch of an infinite proliferating tree. The mathematics is consistent. The branching follows directly from the equations without any additional postulate about collapse. And the theory is completely untestable because by construction, the branches do not interact. You cannot reach the other branches. You cannot verify they exist. Many worlds is mathematically the cleanest version of quantum mechanics and empirically indistinguishable from every alternative. Hidden variable theories take a different position. The probabilities are not fundamental. The universe is deterministic underneath, and the quantum randomness reflects our ignorance of variables we cannot access. David Bohm developed the most worked-out version. Particles always have definite positions. There is a pilot wave guiding them, real and physically present, shaping their trajectories through space. The theory reproduces every quantum prediction exactly. It requires non-locality. The pilot wave connects particles instantaneously across any distance. John Bell proved in 1964 that any hidden variable theory that respects locality cannot reproduce quantum mechanics. Experiments confirmed this. Local hidden variables are ruled out. Non-local hidden variables are still permitted, but they require a kind of instantaneous connection across the universe that sits uneasily with everything relativity tells us about how information travels. What does that tell you? The most successful predictive theory in science requires you to choose between a universe that branches infinitely with every quantum event, or a universe that is fundamentally non-local, or a universe where questions about physical reality before measurement are literally meaningless. Those are not equivalent pictures. They describe profoundly different underlying realities, and there is no experiment that separates them. Every version makes the same predictions about every measurement you can perform. Physicists use quantum mechanics daily. They build semiconductors and lasers and quantum computers with it. They trust the formalism completely because the formalism has never been wrong. Ask them what is actually happening in the experiment, and the room splits the same way the wave function does. We have built the technology of the modern world on a theory whose interpretation, what it is actually describing about reality, has been genuinely contested for 100 years and remains unresolved today. Werner Heisenberg, the man who built the uncertainty principle, allegedly said on his deathbed that when he met God, he would ask about two things: relativity and turbulence, and that he expected God to have an answer for the first one. That is worth pausing on. Heisenberg understood quantum mechanics at a level most physicists never reach. He helped build the theoretical architecture of the subatomic world. And yet, when he thought about the hardest problems in physics, turbulence sat alongside relativity. Not dark matter, not quantum gravity. Turbulence. The thing that makes smoke curl unpredictably from a candle and makes rivers swirl around rocks. Here is why that is not a strange choice. The equations that govern fluid motion have been known since the 19th century. The Navier-Stokes equations are not exotic. They are not quantum mechanical. They contain no reference to space-time curvature or probability amplitudes or string vibrations in 11 dimensions. They describe something as ordinary as water moving through a pipe, air flowing over the surface of a wing, a weather system building over an open ocean. These are the equations of everyday physical reality, written down and verified for nearly 200 years, and we cannot solve them in general. What does that mean exactly? Not that we cannot find approximate solutions. Engineers use those approximations constantly. Aircraft are designed with them. Weather models run on them. What it means is that no one has proven, mathematically, that general solutions to the Navier-Stokes equations always exist, not solved them, proven they exist. That is the problem as it stands today. One of the 7 Millennium Prize problems, each carrying a $1 million reward from the Clay Mathematics Institute, is simply demonstrating whether smooth solutions to those equations always hold, or whether they can break down into something undefined. The prize has gone unclaimed. We do not know if the equations that describe water have solutions in general. That is the situation. Turbulence is where this becomes concrete. When fluid flow exceeds a certain threshold, it stops behaving in ordered, predictable layers and becomes chaotic. Swirling structures form inside larger structures. Energy cascades across scales in patterns that resist calculation. It is not that the physics changes, the same equations apply. It is that the equations become so sensitive to initial conditions, so entangled across scales, that the mathematical tools we have cannot track what they produce. This is why a weather forecast is reasonably reliable at 3 days and nearly useless at 10. Not because the atmosphere does something fundamentally unpredictable, but because the mathematics of turbulent flow amplifies small uncertainties faster than any computation can follow. Here is my position on what that tells us. We have spent extraordinary effort on problems at the quantum scale and the cosmological scale, the Planck length, the structure of space-time at the Big Bang. These are legitimately profound. But the fluid moving through a river, something you can observe, touch, measure at any moment, operates by equations we cannot fully solve. The gap is not in our measurements, it is not in our instruments, it is in the mathematical framework itself. We have the right equations and the wrong tools to work with them. That distinction matters. With quantum gravity, we suspect we may have the wrong theory entirely. With the Navier-Stokes equations, we are fairly confident the theory is correct. The problem is purely mathematical, and that problem has defeated every mathematician and physicist who has approached it for 2 centuries. Physics has unsolved problems at the smallest scale we can conceive. It has unsolved problems at the largest scale we can observe. And sitting between those extremes, at the completely human scale of rivers and weather and air moving over metal, it has a problem that predates both of them and has not moved. We have had the equations for nearly 200 years, and we still cannot solve them in general, which is physics admitting that the movement of water in a river is beyond its current reach. These are not problems at the edges of what physics can describe. They are holes in the center of it. That distinction matters. A gap at the edge means the theory is incomplete in some distant corner, some exotic regime that barely touches the world we inhabit. A hole in the center means the framework is missing something at its foundation. Dark matter and dark energy are not corrections. They are not rounding errors. They are 95% of the universe. Everything physics has built, every equation, every confirmed prediction, every Nobel Prize, was built on the 5% we can actually see. What does it mean to call that a complete picture? Here is the thing about the matter-antimatter problem that is easy to miss. It is not a problem about particles. It is a problem about existence. The physics of the early universe predicts that matter and antimatter should have been produced in equal quantities, and equal quantities annihilate each other completely. If the standard model were fully correct at that moment, there would be no galaxies, no stars, no atoms, no chemistry, no biology. There would be nothing. The fact that something exists, the fact that you can read these words or hear this voice, is direct evidence that the standard model is missing something, not something small, something that determined whether the universe would be empty or full, and we have not found it. Quantum gravity is not an edge case. It governs the Big Bang. It governs the interior of every black hole that has ever formed. Those are not exotic footnotes. The Big Bang is the origin of everything that exists. Black holes are among the most common large-scale structures in the universe. At both of those locations, our two best theories return mathematical nonsense. The equations break down and produce infinities. In physics, infinity is not an answer. It is a confession. It means the framework has failed, and we are staring at the failure directly, and we do not know what to replace it with. Now set that next to the hard problem of consciousness. Here is my position on that. This is not a problem that physics has permission to ignore. It is the problem of what it means to understand anything at all. Every measurement in physics is made by a conscious observer. Every experiment is designed by a mind and interpreted by a mind. And we have no physics of what a mind is, why it experiences anything, or whether subjective experience can be reduced to physical processes. That is not peripheral. That is the ground everything else stands on. Before you can appreciate what these gaps mean together, you need to see what they have in common. None of them are at the boundary. None of them require exotic conditions that rarely occur. They occur at the beginning of time, at the majority of the universe's mass-energy content, at the moment any physicist sits down to interpret data, and at every point where our two foundational theories are asked to work simultaneously. These are the central cases, not the edge cases, and physics cannot describe any of them. What does that tell you? It tells you we are not near the end of something. It tells you we may be near the beginning. There is a historical analogy that physicists have noted and that deserves to be taken seriously. In 1887, the Michelson-Morley experiment set out to measure the Earth's velocity through the luminiferous ether. It found nothing, no ether, no measurable velocity, a clean null result that fit no existing theory. For nearly 2 decades it sat there, sighted and unexplained, while physicists worked around it. Then, in 1905, Einstein published Special Relativity. The null result had not been a failure of the experiment. It had been reality telling the field that a foundational assumption was wrong. The ether did not exist. Space and time were not what anyone thought they were. The entire conceptual framework had to be rebuilt. What we are sitting with now is not one Michelson-Morley result. It is several. Dark matter experiments return null after null. Quantum gravity produces infinities that do not resolve. The matter-antimatter asymmetry is measured precisely and left unexplained. Each one of these is reality pushing back against the framework. Each one is a signal that something foundational is wrong, not peripherally wrong, but wrong in a way that will require the kind of rethinking that produces new physics rather than new parameters. That is what the accumulation of these gaps actually means. Not that the problems are hard, not that we need better instruments, though we do. It means the framework we are working inside is insufficient for the questions we are now being forced to ask. The questions are not at the frontier, they are at the foundation. What the gaps tell us, taken together, is not that physics has almost finished its job. They tell us that the deepest part of the job has not started yet. Every physicist in the field knows these gaps exist. They are in the textbooks, cited in review papers, presented at conferences, and the field proceeds as if they are not the most important thing. That is worth sitting with, not as a criticism of individual scientists, who are in most cases rigorous, careful, and genuinely motivated by understanding, but as an observation about what institutions do when the most important question is also the most dangerous one to ask seriously. Here is the language physics uses. The standard model is routinely described as an effective field theory. That phrase sounds technical. What it means is simpler and stranger. It means everyone in the field agrees this is not the final description of reality. Effective field theory is physicist language for a framework that works within a certain range of energies and scales and is known to break down outside that range. The standard model breaks down at the Planck scale. It breaks down at black hole singularities. It breaks down at the moment of the Big Bang. Physicists know this. They write it openly. They present it at conferences without apparent alarm. And then the field continues refining the standard model and building experiments to test it more precisely within the range where it already works. What does that tell you? Here is the dark part. String theory has absorbed the attention and careers of some of the most mathematically gifted physicists of the last 5 decades. The institutions funded it. The journals published it. Graduate students were advised to work in it. 50 years in, it has not produced a single confirmed prediction about the physical world. Not one. The supersymmetric particles it predicted should have appeared at the Large Hadron Collider at energies the theory itself indicated. They did not appear. The experiment ran, found nothing, and the field's response was not to ask whether the framework was wrong. The response was to propose that the particles are hiding at higher energies and to discuss building a larger collider. The gap was noted. It was cited. The field moved on. Dark matter experiments follow the same pattern. The leading candidate for 30 years was the WIMP. Detectors were built deeper and deeper underground, shielded from every source of interference physicists could identify, cooled to temperatures close to absolute zero, made sensitive enough to register the faintest possible interaction. They found nothing. Each null result ruled out larger portions of the parameter space where WIMPs could exist. The field's response was not to ask whether the assumption driving 30 years of experiments was mistaken. The response was to propose more sensitive detectors and continue the search. That is not unreasonable on its face. Absence of evidence is not evidence of absence. But at some point, the question of whether the assumption is wrong deserves the same institutional energy as the question of how to build a better detector. That point has arguably arrived, and the institutions have not arrived with it. The consciousness question is handled differently, which in some ways is more telling. It is not that the field engages with the hard problem and finds it intractable. The field has largely decided it is not a physics problem at all. It gets classified as philosophy, handed off to cognitive scientists and philosophers of mind, and cordoned off from the domain where the fundamental questions about physical reality are supposed to live. Here is my position on that. A question about why physical processes produce subjective experience is not less physical than a question about why particles have the masses they do. Both are questions about what the universe is doing and why. One of them gets billions in experimental funding, the other gets a departmental boundary. The professional structure of physics is not designed to attack its own foundations. It is designed to extend them. A researcher who spends a career refining measurements within an established framework produces papers, accumulates citations, trains students, and advances through the institution. A researcher who argues the framework is wrong at a fundamental level takes on asymmetric risk. If the critique is correct, the field eventually accepts it, usually slowly, usually after the researcher has spent years fighting for credibility. If the critique is wrong, the cost is immediate and personal. The incentive structure does not point toward the hardest questions. It points toward the questions that can be answered within the existing language. This is not conspiracy. It is not even, in most cases, conscious. It is what happens when institutions optimize for continuity and individual researchers optimize for career survival. And both of those optimizations are individually rational, and the collective result is a field that knows its foundations are cracked and continues building upward. What happens to any structure built on a cracked foundation if no one is professionally incentivized to examine the crack? The asymmetry is exact. The cost of attacking the foundations falls on the individual, and the cost of not attacking them falls on everyone, which is exactly the calculation that produces 50 years of mathematically beautiful work with no testable predictions. The history of physics is not a story of accumulation. It is a story of frameworks that worked perfectly until they didn't, and then broke completely and were replaced. Newtonian mechanics described everything observable for 2 centuries: planets, pendulums, projectiles, tides. Engineers built bridges and cannons with it. It was not approximately correct. It was exactly correct for every measurement anyone could make. Then the instruments got better. Then the Michelson-Morley experiment in 1887 tried to detect the motion of Earth through the luminiferous ether and found nothing. No ether, no motion detectable, a null result that the framework had no room for. 18 years later, Einstein published special relativity, and the Newtonian framework did not get extended. It got replaced at its foundations. The physicists who declared physics nearly complete in the 1890s were not careless. They were working inside something that genuinely worked for everything they could reach. The crack was real. They just could not see what it was pointing at. Classical electrodynamics had the same shape: elegant, unified, precise. Then the ultraviolet catastrophe. Hot objects were supposed to radiate energy across all frequencies according to classical theory. The math was solid. The prediction was catastrophic. A perfect blackbody should emit infinite energy at high frequencies. That is not a rounding error. That is a theory telling you something is fundamentally broken. Planck patched it in 1900 with a mathematical fix he himself found uncomfortable. Einstein explained the photoelectric effect in 1905 with discrete quanta of light. By 1927, the entire classical picture of matter and energy had been dismantled and rebuilt as quantum mechanics. Not corrected, rebuilt. Here is what those two episodes have in common. The frameworks did not fail at the edges. They failed in specific, measurable, reproducible ways that could not be accommodated within the existing structure. The failure was precise, and the replacement was not a modest extension. It was a deeper description that contained the old framework as a special case while operating on entirely different assumptions about the nature of reality. That is the pattern. That is what a revolution in physics looks like from the inside. Now look at where we are. The universe is 95% invisible, and the leading candidates for what that 95% consists of have been ruled out by experiment after experiment. The two most successful theories in physics cannot be reconciled with each other, and the places where they conflict, black hole interiors, the Big Bang, are not exotic edge cases. They are foundational. The matter-antimatter asymmetry is not a footnote. It is the reason anything exists at all, and the standard model cannot account for its magnitude by orders of magnitude. These are not loose ends. They have the same structure as the ultraviolet catastrophe: precise failures, reproducible contradictions, things the framework has no room for. The experiments running now are collecting the data. Dune will fire neutrino and anti-neutrino beams through 800 miles of Earth beginning in 2026 and look for asymmetries in their behavior that might explain why matter survived. Next-generation dark matter detectors are pushing sensitivity into regions where the leading theories have nowhere left to hide. Gravitational wave observatories are building the baseline for signals from the early universe that carry information about conditions at energies we cannot reach with particle accelerators. Quantum computers are beginning to probe the foundations of quantum mechanics in ways that were not possible a decade ago. These instruments are the Michelson-Morley experiment of this era. They are looking for something. Some of them will find null results that rule out the remaining candidates for dark matter. Some will find unexpected signals. Most of what they return will be filed, processed, and analyzed within the existing frameworks, and it will fit, mostly. And somewhere in that data, almost certainly, there is the crack. The person who sees it may already be reading those results. They may be a graduate student somewhere looking at an anomaly that everyone else has attributed to systematic error. They may be a theorist who has noticed that two separate null results taken together imply something that neither experiment was designed to test. The history of physics suggests they will not be the most senior person in the room. It suggests the crack will not look like a crack at first. It will look like a problem with the measurement. The person who sees what the current cracks are pointing at has not published yet, and when they do, everything we think we know about reality will need to be rebuilt from a deeper foundation, and we will not have seen it coming.